In this video, we're going to talk about buffer systems, which are mixtures that regulate the pH when a strong acid or a strong base are added to them. In order to set this up, we have to talk a little bit about reactions between acids and bases. And there are some categories of these reactions. The first one let's look at is strong acid reacting with a strong base. So let's say, for example, we have sodium hydroxide and hydrochloric acid reacting with each other. This is the strong acid. It's going to donate a proton. The proton is just the H from the HCl. If you look at the ionic reaction, this is Na plus OH minus plus H plus Cl minus. And on the other hand, you're going to have H2O and you're going to have Na plus Cl minus. Those are spectators, chloride and sodium. And so the overall reaction is just water being formed from it, the ions. K for the reverse reaction is 1 times 10 to the minus 14. So for this reaction, it's 1 over 10 to the minus 14, which is practically infinity for all practical purposes. So we can think about this reaction as going to completion. In trying to think about the results of acid-base reactions and what is present in a mixture, it's important to think about something called the major species. So the major species are just what is there in significant concentrations in the mixture. So here we have 0.1 molar HCl and 0.2 molar NaOH, equal volumes of each one. So let's think about the non-spectators here. If we take 500 times 0.1, that gives us 50 millimoles of H plus. And 500 milliliters of 0.2 molar, well, that's going to give us 100 millimoles of OH minus. And the overall reaction, remember, is OH minus, and H plus is giving us H2O. And we can think about a before change after chart here. If we have 100 millimoles and 50 millimoles, and the stoichiometry is 1 to 1, we're going to lose 50 millimoles of each. We're going to gain 50 millimoles of water. So we won't end up with any H plus, not a significant amount, but we will end up with 50 millimoles of OH minus still present in the solution. So in this mixture, we will have water, of course, that's the background, that's the most major species. We will have all of the Na plus and all of the Cl minus that were there. They're not a contributor to pH, but they're there. And we are going to have still a significant amount of OH minus left in the solution. Now let's look at a strong acid, weak base mixture. This is what the weak base is going to do. In aqueous solution, there's going to be a reversible ionization to give you the conjugate acid, Hb, and some hydroxide ion. K for that is just whatever the Kb is, which is going to be a fairly small number. The strong acid is going to grab those OH minuses that are released and do a one-way reaction with them to form water. K for that reaction, as we have discussed, is practically infinity. If we add these reactions together, here's what we get. Spectators that drop out, OH minus and water. And by the rule of multiple equilibria, the K for this reaction is going to be the Kb for the weak base times practically infinity. So this can be thought of as a one-way reaction where H plus reacts with the weak base and makes the conjugate acid. So a strong acid weak base reaction is also going to go to completion. Here's another major species question. What are the major species in a mixture of 250 milliliters of 0.01 molar NH3, that's a weak base, and 125 milliliters of 0.01 molar HCl, and that's a strong acid. So what's the overall reaction? Well, it's NH3, the weak base, reacting with the H plus from the HCl and producing NH4 plus. Let's do a before change after thing. How much NH3 is there? 250 milliliters times 0.01 moles per liter gives us 2.5 millimoles. 125 milliliters of HCl times 0.01 moles per liter gives us 1.25 millimoles, and there's no ammonium ion before the reaction takes place. Change, since this is a one-way reaction, we're going to use up all 1.25 millimoles of H+. We're going to use up an equivalent amount of NH3, because it's one-to-one stoichiometry, and we're going to gain an equivalent amount of millimoles of NH4. So after this change takes place, we don't have really any H plus. We are going to have 1.25 millimoles of NH3 and also 1.25 millimoles of NH4 plus. So what are the major species after this reaction occurs? Well, we're going to have a bunch of NH3. Well, there's going to be water, of course. There's going to be NH3. There's going to be some NH4 plus, and then there's going to be some chloride ion as well, which was the spectator when the H plus ionized. Now let's look at a strong base weak acid mixture. Here's what the weak acid is going to do. It's going to ionize to produce H plus or hydronium ions and A minus. K for that is whatever the Ka is for the acid. The strong base is going to react with the H plus created here and do a one-way reaction to make water. K for that is about infinity. Add these together. K is Ka times infinity, which is a very large number. H plus is a spectator here. And the overall reaction is OH minus reacts with the weak acid and produces its conjugate base and some water. And we can think about this as a one-way reaction because K is very large. So a strong base weak acid reaction is also going to go to completion. Here's another major species question. We have some HNO2, weak acid, and NaOH, a source of OH minus, and it's going to make NO2 minus and water because the strong base is going to attract that proton. We have 250 milliliters of 0.1 molar HNO2, so that's 25 millimoles. We have 125 milliliters of 0.1 molar NaOH, so that's going to be 12.5 millimoles. And before this reaction occurs, 0 and 0. Well, water's not really 0. We just don't care about it. That's the before line. The change, one-to-one stoichiometry, and a one-way reaction means we're going to lose 12.5 millimoles of both reactants. We're going to gain 12.5 millimoles of both products, so that afterwards we're not going to have really any OH minus. We're going to have 12.5 millimoles of HNO2 and also 12.5 millimoles of NO2 minus, and water will be a very large amount. Now, it's not true that there's no OH minus present because NO2 minus is a weak base, and so it is going to produce a tiny amount of OH minus, but not very much. So the major species here are, of course, water, and we have the sodium from the sodium hydroxide, that's a spectator, and we are still going to have some HNO2 left, and we are still going to have some NO2 minus left in this mixture. Now let's look at a weak base, weak acid mixture. This is the only one we have left. It's the only possible combination. Here's the weak acid. It's going to produce H plus and A minus reversibly. K for that is Ka for the acid. Here's the weak base. It's going to react with water to produce Hb plus and OH minus. K for that reaction is Kb. If we add these together, K is still a small number. Ka times Kb is going to be the product of two fairly small numbers because it's a weak acid and a weak base. We can net out water from both sides because OH minus and H plus are not going to exist separately. So that part of this reaction is going to shift completely to the left, and any stray H plus and OH minus, except for very small quantities, are going to cancel out. They're just going to become water. So the net ionic reaction for this is the weak base reacts with the weak acid and produces the conjugate base of the acid and the conjugate acid of the base, and K for this reaction is going to be very small. So weak base, weak acid reactions are not going to reach completion like the other reactions that we looked at. Here's another major species question. We have 250 milliliters of 0.1 molar HF and 250 milliliters of 0.1 molar NH3. What's the overall reaction? Well, HF is going to react with NH3, and reversibly it's going to produce the conjugate base of HF, which is F minus, and the conjugate acid of NH4, which is 1 plus. Remember, K is going to be very small, so this reaction isn't going to go very far to completion. So because we are not going to produce very much F minus, And we are also not going to produce very much NH4 plus. This reaction is going to mostly consist of, when it reaches equilibrium, the water that's the background for everything, and HF, and NH3, and very little of anything else. Another topic to talk about before we start really defining buffers is the acid-base properties of salts. If the cation in a salt is the cation that comes from a strong base, so these are the hydroxides like NaOH or KOH or CaOH2, something like that. If it's one of those, which basically means group 1 and some group 2s, it is not going to affect the pH of the system. Here's the reason for that. NaOH completely dissociates, because it's very soluble, into Na plus and OH minus. K for that is essentially infinity. It's a very large number. So that means for the reverse reaction, where OH minus would get together with Na plus and produce NaOH, thereby decreasing the pH, that's not going to happen, because K would be, for that reaction, essentially 1 over infinity, which is about 0. And so that means this reaction is not going to occur, so one of those salts is not going to trigger a change in pH. Another type of cation that you might have is the conjugate acid of a weak base. That will tend to lower the pH of the system. Here's an example. If your salt was ammonium chloride, NH4Cl, NH4 plus, that is the conjugate acid of NH3, a weak base. And because it's going to function as an acid, it will do its thing. NH4 plus is going to dissociate and give you some H plus and some NH3. And so that means it's going to lower the pH by increasing the concentration of H plus. Now we have to look at anions, and there's 3 different cases here. If the anion is the anion of a strong acid, it does not affect the pH of the system. And this is very similar reasoning to why the cation from a strong base doesn't affect pH. HCl dissociating into H plus and Cl minus is essentially a one-way reaction. So to go in the other direction and take H plus out of the system and raise the pH, that would require shifting to the right when K is essentially 0. So anions from the strong acids, and there's only 6 of them, remember, so these we're talking about Cl minus, I minus, Br minus, NO3 minus, SO4 2 minus, and then also ClO4 minus. Those are the anions from the 6 strong acids. If that's the anion in your salt, that is not going to affect the pH of the system. Another case you could have is an anion could be the conjugate base of a weak acid. If that's the case, like all bases, it would tend to raise the pH of the system. Here's an example. Sodium acetate is a salt. When it dissolves in water, it produces the acetate ion. That is the conjugate base of HC2H3O2, which is acetic acid. So that means it's going to do its thing, react with water, produce a little bit of that acid, but it's also going to produce OH minus, and that's going to raise the pH of the system. The last case is the anion itself could be a weak acid. If that's the case, it's going to tend to lower the pH of the system because it's going to do its acid thing and produce more H pluses in the solution. An example of this would be sodium biphosphate or sodium dihydrogen phosphate. It produces this H2PO4 minus ion, but that is an acid. And so it's going to dissociate, give you HPO4 2 minus, and release some H plus into the system. These are pretty easy to spot because they start with H. Anions that start with H, they're weak acids themselves, and they're going to lower the pH of the system. So now let's kind of summarize. There's 2 kinds of cations. Either they come from a strong base and they have no effect on pH, or they are the conjugate acids of weak bases. In that case, they're going to tend to lower the pH. We could have anions from strong acids, for example, chloride or nitrate. Those will have no effect on pH. We could have acidic anions. These start with H, so they're pretty easy to spot. These things are, because they're acids, going to tend to lower the pH. All the other anions are going to be conjugate bases of weak acids, and so they're going to tend to raise the pH of the solution. So let's look at some examples. What if our salt was calcium nitrate? This is going to dissociate, and it's going to give you calcium ions and NO2 minus ions. This is going to have no effect because it's the cation from a strong base. But NO2 minus does not start with H, and it's not the anion from a strong acid. So that means it's one of those weak bases. In fact, it's going to react with water, and it's going to produce some HNO2, and it's going to produce a little bit of OH minus, and that's going to raise the pH. So this has no effect. This has the effect of increasing pH, so that's what's going to happen. Next example, NaCl. Well, when this dissolves, it's going to give you Na plus ions and Cl minus ions. This is the cation from a strong base, no effect on pH. This is the anion from a strong acid, no effect on pH. The overall result, no effect on pH. NH4Br. When this dissolves, it's going to give you NH4 pluses and Br minus. This is the anion from a strong acid. That's going to have no effect. NH4 plus is the conjugate acid of NH3. So what it's going to do is it's going to dissociate and give you some H plus and some NH3. That's going to lower the pH. So this lowers pH. This doesn't do anything to pH. Overall, the effect is going to lower pH. It's an acidic salt. KHCO3. This is going to give you K pluses and HCO3 1 minuses. This is the cation from a strong base. No effect on pH. This is an anion that starts with H. That's going to lower the pH because it's a weak acid. HCO3 minus is going to ionize to give you H pluses and CO3 2 minuses. That will lower pH. So this is an acidic salt. Here's NH4NO2. This is going to give you NH4 plus, and it's going to give you NO2 minus when it dissolves. This, as we have already seen, will tend to lower pH because it's a weak acid. It's a conjugate acid of NH3. This will tend to raise pH because it's a weak base. We saw that up here. So in a case like that, we have to make a comparison. For NH3, Kb is 1.8 times 10 to the minus 5. So that means for NH4 plus, Ka is Kw divided by 1.8 times 10 to the minus 5. Kw is 1.0 times 10 to the minus 14. And so this ends up being 5.6 times 10 to the minus 10. Ka for HNO2 is 4 times 10 to the minus 4. So that means the Kb for NO2 minus is going to be Kw divided by that number. And that ends up being 2.5 times 10 to the minus 11. Since the Ka for the acid in this mixture is bigger than the Kb for the base, that means this is going to be overall an acidic solution. Most of the time you don't have to make that complicated of a comparison. It's usually pretty clear. Okay, we're finally set up now that we can start talking about buffers. When a mixture contains an acid and it also contains its conjugate base, it resists changes in pH. For example, if a mixture contains both HF and F minus, then this equilibrium exists. What happens if we add H plus to the system? Well, by Le Chatelier's principle, we can see what's going to happen is it's going to shift to the left. And that strong acid, H plus, is going to be turned into a weak acid, HF, and that's going to resist having the pH drop a lot. What's going to happen if OH minus is added to the system? Well, two things are going to happen. First of all, OH minus is going to react with H plus to produce water, and that's pretty much a one-way reaction. That's going to reduce the concentration of H plus, and that is going to cause a shift to the right. So that's going to take your strong base, the OH minus, and in two steps it's going to turn it into a weak base. So add those two steps together and this is what you get. OH minus is going to react with HF and it's going to produce, it's going to go in a one-way reaction, pretty much, H2O and F minus. Strong base turns into weak base and that keeps the pH from rising rapidly. The rest of this video is going to be about doing some calculations to find out what are the pHs of buffers, and after doing a few example problems, we're going to come up with an important kind of a shortcut that allows us to do buffer calculations much more easily than we will with these introductory problems. The first question we have is, what's the pH of a buffer that's made from 0.1 molar HNO2, the Ka is given, mixed with 0.1 molar NaNO2. So that's a source of NO2 minus, which is the conjugate base of that weak acid. So that's going to make this a buffer. Let's switch to a workspace that has more room to work and work out some of these problems. To get started, let's make a rice chart. Here's the equilibrium that will be established. It's HNO2 in equilibrium with H plus NO2 minus. Initially, we have 0.10 molar HNO2 and also 0.10 molar NO2 minus. The stoichiometry is all 1-to-1 here, so this is going to be a minus X, a plus X, and a plus X. At equilibrium, this will be 0.10 minus X, this will be X, and this will be 0.10 plus X. So Ka, which is 4 times 10 to the negative fourth, will be equal to X times 0.10 plus X, that's the NO2 minus concentration, divided by 0.10 minus X as the HNO2 concentration. 10 to the minus fourth is pretty small, and that's always going to be the case for these weak acids. And so that means that X is ignorably small compared with 0.10. So this simplifies to 4 times 10 to the negative fourth is about equal to X times 0.10 over 0.10, or X is 4 times 10 to the minus fourth. So the pH would be equal to the negative base 10 logarithm of 4 times 10 to the negative fourth, which turns out to be 3.40. So that's the pH of that buffer. Let's solve a couple more problems to see the effect of this buffer. First question is, what is the pH change if 10 milliliters of 0.1 molar HCl is added to 1,000 milliliters of water? So if it's ordinary water, then that means the starting pH is going to be 7. After we add the HCl, we will have added 10 milliliters times 0.10 moles of H plus, because it's a strong acid, per liter, and this gives 1.00 millimoles of H plus. So that means the concentration of H plus in this solution is 1 millimole over the volume, which is now 1,010 milliliters, because we added 10 milliliters to our 1,000 milliliters. And that works out to 9.9 times 10 to the negative fourth moles per liter. And so if we take the negative base 10 logarithm of that, that gives us our pH, which rounds off to 3. So the pH change is negative 4 points. The next question asks, what is the pH change if 10 milliliters of 0.10 molar HCl, so that's the same amount of acid, is added to 1,000 milliliters of not water, but the buffer that we created before? Well, if we have 1,000 milliliters of that buffer and we mixed equal quantities, then that means the concentration of HNO2 initially and the concentration of NO2 minus in our buffer initially will be equal to 500 milliliters, because we would have had 500 milliliters of each, times the concentrations that we added, 0.10 moles per liter, and that ends up being 50 millimoles each. So now what's going to happen is we're going to have a one-way reaction where NO2 minus, the conjugate base, is going to react with the H plus, and this will be a one-way reaction, and it'll produce HNO2. Because it's a one-way reaction, we'll use a BCA chart. We had 50.0 millimoles of NO2, and then we can see from our calculation above here that we start out with 1 millimole of H plus, and we are also going to have 50 millimoles of HNO2. The limiting reactant is the H plus, so we're going to lose a mole of H plus, a millimole of H plus from both reactants, and we're going to gain a millimole of HNO2, so that afterwards this comes down to 49.0 millimoles. There won't be any H plus left, and this will go up to 51 millimoles. So that means our HNO2 concentration is going to be 51 millimoles in 1,010 milliliters. And this comes out to 0.050 molar. Concentration of NO2 minus, that's going to be 49 millimoles over our 1,010 milliliters. And that comes out to 0.048 molar. So if we go back to our Ka expression, 4 times 10 to the minus 4 is going to be equal to x times about 0.408, because we're going to ignore the x, divided by 0.050, and that comes out to 4.2 times 10 to the negative fourth. And if we take the negative base 10 logarithm of that, we get our pH, which is 3.38. But remember, the pH of our buffer was 3.4. So we have a pH change of minus 0.02 pH points. Compared with the water, when the same amount of acid was added, it dropped by 4 entire pH points. So the buffer did its job. It effectively resisted the change in pH, even though the same quantity of a large acid was added, from going down by 4 points to only 0.02 of a point. Mixing an acid and its conjugate base together are not the only way to create a buffer. You can also create a buffer by a reaction that produces the conjugate base or the conjugate acid. For example, if we take a strong acid and add it to a weak base, it's going to create a buffer. Here's the reaction that's going to take place. H plus, the strong acid will be the source of that, is going to react with our weak base, and it's going to produce, in a one-way reaction, Hb plus. Now, in order for this to happen, we have to have an excess of base, because we still have to have some base left, and then we will have its conjugate acid present in the system as well. Let's take a look at an example. What's the pH of a buffer created when 0.0050 moles of HCl is added to 100 milliliters of a 0.1 molar NH3 solution? And the Kb for NH3 is given here. If we have 100 milliliters of our base solution and its concentration is 0.10 moles of base per 1,000 milliliters, this is going to give us 0.0100 moles of our base. Let's figure out what happens here when the acid is added. The H plus is going to react with the weak base, one-way reaction because it's a strong acid weak base, and that's going to give us NH4 plus ions. Let's do a BCA chart. Initially, we have 0.0050 moles of H plus. We have 0.0100 moles of NH3, and we don't have any NH4 initially. The change, our limiting reactant is the H plus, so we're going to lose 0.0050 moles of each reactant, and we're going to gain 0.0050 moles of product. So afterwards, no H plus, this drops down to 0.0050, and this goes up to 0.0050. And so now we have a base and its conjugate acid both present in the same solution. We just created a buffer. Now let's find out what its pH is. NH4 plus is going to be in equilibrium with H plus and NH3. The initial concentration of NH4 plus and NH3 is going to be our 0.0050 moles in our 100 milliliters, which is a 0.1 liters. So this ends up being 0.0500 molar. So in our initial concentration, both NH4 plus and NH3 are going to have those concentrations. No H plus. And then the change takes place. We're going to lose X, gain X, gain X, one-to-one stoichiometry. So this is 0.0500 minus x, x, and 0.0500 plus x. So Ka for NH4, which is going to be Kw divided by the Kb for NH3, is equal to H plus concentration, which is x, times the base concentration, 0.0500 plus x, over the acid concentration, which is 0.0500 minus x. But this is going to be equal to 1 times 10 to the minus 14th over the Kb, which was 1.8 times 10 to the minus 5, and that's going to be 5.6 times 10 to the negative 10th, which is a very small number. So the simplification of leaving off those x's will be definitely viable. So 5.6 times 10 to the negative 10 is equal to x times 0.0500 over 0.0500, which just means x is 5.6 times 10 to the minus 10th. And that is the H plus concentration, because that's what that line means there. So we can use that to figure out pH, and the pH is going to be negative base 10 logarithm of 5.6 times 10 to the minus 10, which is 9.26. Similarly, a strong base reacting with a weak acid also creates a buffer. Here's the reaction. The weak acid is reacting with the OH minus from the strong base. It's a one-way reaction because weak acid, strong base is one way. And that's going to make water, and it's going to make the conjugate base of that weak acid. So now the weak acid was present, and now we have some conjugate base as well. But again, this is only a buffer if the HA is in excess and the OH minus is the limiting reactant. So let's take this example. If we mixed KOH, a strong base, with acetic acid, HC2H3O2, how does this buffer against a strong base? Let's going to set up a situation where our HC2H3O2 is that, and C2H3O21 minus is that. So when we add our strong base, the reaction that will happen is the OH minus from the strong base will react with the acid, C2H3O2, and it'll produce C2H3O21 minus, and we have converted strong base into weak base. How does it buffer against added strong acid? Well, we have acetate ion in here as well. So if a H plus is added, then it's going to react with C2H3O21 minus, and it's going to produce acetic acid, HC2H3O2. So strong acid got turned into weak acid. There's an important shortcut here called the Henderson-Hasselbalch equation. We've been setting up a Rice chart and making a simplification, but we can always make that simplification. If we have a generic buffer made from some weak acid HA and its conjugate base A minus, and we want to know what is its H plus at equilibrium, looking at this Rice chart, we start out with some starting concentrations of HA and A minus, 1-to-1 stoichiometry typically. So that equilibrium, we're going to have HA initial minus X for the HA concentration. And for the A minus concentration, we're going to have the A minus initial concentration plus X, and then H is going to be X. So when we put that together, if you make the simplification that X is small compared with the initial concentrations of both the acid and its conjugate base, which is almost always a good assumption because Ka is going to be a small value, then H plus is going to be equal to Ka times the ratio of the acid concentration initially to the base concentration initially. Now let's do something. Let's do the P function on both sides. So on the left-hand side, we got minus log H plus concentration. On the right-hand side, we're going to have minus log of Ka plus minus log of HA concentration over A minus concentration. The minus log of H plus, that's pH. If we take the negative log of Ka, that's a value called pKa. It's the P function. And then we could change the minus into a plus sign and flip HA and A minus concentrations upside down. So this is A minus on the top and HA concentration on the bottom. And now we have a log form of the Henderson-Hasselbalch equation, which is often much more useful. And then we can do another thing too. Because the H plus and the A minus are in the same volume, because they're in the same mixture, the ratio of the concentrations of both of these things is going to be the same, and it just cancels out. So we could write this either way. pH equals pKa plus log of concentration ratios, or number of moles of A minus, or number of moles of HA as well. And that's often much more useful. Now, these are initial values because we're making the assumption that there's not going to be a significant change compared with the initial concentrations. So let's look at a particular case. What is the pH of a buffer in which the concentration of the conjugate base and the acid is the same? If that's the case, then this is just 1. That ratio is 1. Log of 1 is 0, so that means the pH in this case is just equal to pKa. Let's work out an example problem where that isn't the case. What's the pH of a buffer made by mixing 50 milliliters of 0.1 molar acetic acid and 50 milliliters of 0.2 molar sodium acetate? So the number of moles of acetic acid, HC2H3O2, that's going to be equal to 5 millimoles, because we're taking 50 milliliters times 0.1 mole per liter. The number of moles of acetate ion, C2H3O2 1 minus, that's going to be equal to 10 millimoles, and that's because we're taking 50 milliliters times 0.2 moles per liter. What's the pKa? pKa for this acid is negative base 10 logarithm of 1.8 times 10 to the negative 5, which is 4.74. So now this gets plugged into there, and then we can use these numbers of moles to create our ratio. That's the conjugate base, and that's the acid. So our pH is going to be equal to 4.74 plus the base 10 logarithm of 10 millimoles over 5 millimoles, and this comes out to 5.04. Now let's look at what is the pH change if 2.5 milliliters of a 0.1 molar strong base solution is added to that same buffer. This is describing the same buffer that we just worked out the pH for. So now let's set up a BCA chart. Well, the reaction that's going to happen is the conjugate acid, HC2H3O2, is going to react with this strong base in a one-way reaction, strong base, weak acid. It's going to make water, and it's going to make C2H3O2 1 minus. We initially, remember, had 5 millimoles, this is our before line, of acetic acid. And we had 10 millimoles of acetate ion, water we don't care about. Hydroxide ion, well, we took 2.50 milliliters of 0.10 moles of OH minus per liter, and this gives us 0.25 millimoles. So that's at 0.25. That's our change. Hydroxide ion is the limiting reactant, so we're going to lose 0.25 from both reactants. We're going to gain 0.25 on the product side. Afterwards, 4.75 millimoles is the amount of acetic acid. We won't have any OH minus, don't care about water, and we're going to have 10.25 millimoles of acetate ion. So what's our pH? The pH is the pKa, which remember is 4.74 for this acid, plus the base 10 logarithm of base on top, 10.25 millimoles, acid on bottom, 4.75 millimoles, and that calculates out to 5.07. The initial pH for this buffer before that acid was added was only 5.04, so even though we added a strong base, the pH only went up 0.03 of a pH point. The Henderson-Hasselbalch equation really simplifies things because all you have to know is what the number of moles are for the acid and base or their concentrations, and you just plug them in and it does the work for you.